I think we should get our program started for this afternoon. My name is Bill Sharp. I'm the chair of the Society of Analytical Chemists of Pittsburgh Water Symposium Committee, and I'll be your presider for this afternoon. Just a couple of things you probably saw flashing up there, and there they are, so please pay heed to those so that we don't have any interruptions during our program. This is the golden anniversary of the James L. Water Symposium. Back in 1989, Mr. Waters proposed that the SACP offer an annual symposium describing the origin, development, implementation, and commercialization of scientific instrumentation of established and major significance. And certainly, we have a classic example of that this afternoon. All the expenses of the Water Symposium are generously provided by Mr. Waters. Unfortunately, he had some business commitments that he couldn't be here today, and he promised he'd be with us this time next year in New Orleans for the 26th Water Symposium. So we thank him and we wish him well. The golden anniversary of the Water Symposium recognizes the development and commercialization of MALDI-TOF. The 5 speakers selected for today's symposium are pioneers in this area and are uniquely qualified to discuss the development and commercialization of MALDI-TOF. These speakers will also talk about the current state of the technique in its future. So without any further ado, let me introduce our first speaker this afternoon, and that would be Peter Roepstorff from the University of Southern Denmark, and he will talk about peptide and protein mass spectrometry before MALDI and ESI, the pioneering Peter. Peter?
Thank you very much. And first of all, I would like to thank the organizers for inviting me here, and especially my friend Marvin Vestal, who I think was the one who pointed at me. It's a real honor to speak here. And I was given the task to talk about the time where we could not do anything with mass spec on peptides and proteins. But what I will try to show you is that we can do something. But before that, I will say that I've always been, my incentive to go into science, that's nature. And that's where I live in Denmark, a winter picture, but it's not as cold as Chicago. And what I will tell you about is what happened in the early times. And the very first mass spectra of peptides, that dates back to 1959 to 60, where Klaus Biemann showed he could make spectra of peptides after extensive derivatization, and Stenhagen in Sweden and Ryhage, they also showed that it was possible to make spectra of this. And that meant that it was a time when mass spec started to be used mainly in organic chemistry, and a number of groups worldwide tried to look a little at peptides and proteins after derivatization. We had in Russia a group headed by Shimyakin and with Orshinikov and others. We had in Germany a number of groups, Heinz and Grünsmacher. We had Weigand and Prox. We had Koenig. All of them made some peptide mass spectra. In England, we had Agarwal and Kenner in Liverpool, Ablin and Jones from Oxford, and at AEI, we had in Manchester, we had Barber and Wolstenholme. And in the US, beside of Klaus Biemann, we also had Fred McLafferty and Desiderio and Young and Zwick. They all published in the late 60s, beginning of the 70s, spectra of peptides, mass spectra. But all these studies were made on small derivatized synthetic tetrapeptides, and it was really a matter of trying to establish the fragmentation pattern. It was not in any way biological applications. The first real interesting biological applications, that was a paper from Mickey Barber and the French group in Lederer's group in France from 1965. And that was also what was setting me off in mass spec, because at that time I had a problem. I had designed or built the first fully automated peptide synthesizer in the world. But my problem was that whatever came out of it was not very active. And I couldn't figure out with the means we had what went wrong. And then I was reading this paper where they determined the structure of a very fortuitous compound, fortuitine, by mass spectrometry. And I didn't have any idea what mass spectrometry was, but I was reading this paper 10 times, and I said, that's what I want to do. And if you look at it, it was made by electron impact on an AEI MS9 mass spectrometer, and just look at the error, mass error on the fragment ions. That's just what we now can do again. So it was quite impressive, and it was a quite large peptide. It was natural derivatized. It had a heterogeneous acylation group at the N-terminus. It was partially methylated, and it was also partly methyl-esterified. So it was naturally derivatized. But I mean, that was really a breaking thing to see that it was possible to determine the structure of a natural peptidolipid of that size with mass spectrometry. And that was setting me off. The other thing, that was Beeman. Beeman was going for the the GCMS of derivatized peptides, where he reduced them to amino alcohols and trimethylsilylated, and then he could deal with quite complex mixtures, but only, let's say, up to tetrapeptides. That was the maximum size he could get through the gas chromatograph. But also that was quite impressive. And he came with a statement in a paper from '66, where you see here, which is kind of one of the most prophetic statements I have seen in any scientific paper in our field, where he said, in view of the small amount and so on, where using a computer, you would be able to analyze peptides generated by partial acid hydrolysis from larger peptides derived by enzymatic cleavage, and you could then do the sequencing. And I mean, that's a statement from 1966. That's what's the fact today, but it has not really been before that. I think that's a very prophetic statement. The thing with the fortuitine, that was that it was naturally N-methylated, and that made Boupestache from the French group to start to derivatize the peptides by permethylation, and it showed up that they gave very nice sequence ladders throughout the spectra. You could directly from an electron impact spectrum read the sequence, and as a matter of fact, with a little training, when you had the numbers in head, you could sit directly and read it. We didn't have a computer at that time. It was printed out on photographic paper, but you would just run down. The only problem was to get masses, because you had to count all your way up in the spectra and put on masses on the spectra. I got my first mass spectrometer. I applied for my first mass spectrometer in '67, and I got my first mass spectrometer in '68, a small magnetic sector instrument, which was designed, as a matter of fact, by Beeman and produced by Perkin-Elmer. And it had a mass range of up to 2,000 in mass, but it could. The advantage was it both had the gas chromatograph, which would say I could use a Beeman type, but it also had a solid inlet probe, so I could use these permethylated derivatives. And I immediately started to try to get it to work. At that time, there was no installation engineers. There were no information whatsoever, and I had never seen a mass spectrometer before. So it was uncharged in the courtyard, and I had to, in some way, to get it up on the fourth floor and to get it to work. It took me a little time. But we rather soon realized that whenever we had some of the amino acids, like methionine, for example, then we got protonization, and then they were not volatile. So I first tried to solve that problem back in time. It was still electron impact mass spectrometry. And you see, this is an acetylated and methyl esterified, and this is the same one, permethylated, after we protected the methionine, which is sitting there, with oxidation during the reaction. And you can see very nice set of peaks, which just makes it very easy to read the sequence. But I mean, when I applied for this mass spectrometer, I couldn't argue. I was very young, only 25 years old, 25 years old, and I could not argue just based on my problem with my synthesizer. This problem was solved immediately when I got my first mass spectra, because it was trifluoacetylation going on during the synthesis. But I had to find a better argument, and my postulate was that proteins had to be modified. And that, for some or another reason, our research councils bought that idea, and since then I have been hunting post-translational modifications to prove that I was right. And the first one we came up with was the gamma-carboxyglutamic acid in the prothrombin, which you see here, which that's in the blood clotting proteins, and that was the proof that we could find post-translational modifications using mass spectrometry, still with electron impact mass spectrometry. And a number of other groups also started to look for modifications with mass spec at that time. Beside of me, it was mainly Howard Morris in late in Oxford and later at Imperial College who took up the permethylation. We, as a matter of fact, were both being taught how to do in Poupet's laboratory in Paris back in time. But the other problem we had was that we had no sensitive way of separating peptide mixtures. So I designed a way, because when you have this spectra, you can cross over when you have a mixture from one sequence to the other, and at the end you don't know where you are. And if you look at here, this is a rather simple mixture of a few peptides only. If you just make a single spectrum, you get a hell of a lot of possibilities when you try to interpret the data. But if you combine a normal derivatization with a derivatization with deuterated reagents, and you make one step of Edman degradation, then you are down here, you just have the number of possibilities which are there. And that allowed this. And as a matter of fact, that was something I presented in the International Mass Spec Conference in Edinburgh. And at that time, Fred McLafferty, he came afterwards to discuss with me. And since I didn't know anyone in the field, I felt that now the sun had been shining on me. The big McLafferty had been arriving to discuss my lecture with me. So that was a fantastic moment in my career, I would say. But at that time also, we had other techniques coming up. We had chemical ionization and we had field desorption. Chemical ionization was, it was Frank Field who started it up, but it was Henk Fales in Bethesda who had started to look at peptides. And I went to him after seeing this spectrum, which I made together with Kuryshkin from the Russian group. And we tried to see if we could push the limits by using chemical ionization. But we still had the need for getting these samples volatile, so it didn't push very much. Then we had field desorption with Beckay in Bonn, and I also went down there immediately. There we could use underivatized peptides, and we believed this would be the way to go. But it was not very practical, because the desorption took place in a fraction of a second when you were heating up a wire in this system. And you had to be extremely lucky to be in the right place of the scan to catch your peak. So sometimes you had to try 20, 30 or more times before you managed to get a mass. So that also was not very practical. And so we continued to do electron impact mass spectrometry of the derivatized peptides, and we found other modifications. This is the beta-hydroxy aspartic acid and another of the proteins having gamma-carboxyglutamic acids together with a Swedish group. And that was a real challenge, because if you look at this spectrum, they are extremely complex. They should be simple because of derivatization. But it shows up that there are 3 different parallel spectra in that, because we have loss of the N-terminal part with the McLafferty rearrangement and some other reactions. So in principle, that's a mixture of 3 different samples which then end up with the right thing. But at that time, to make a real good mass spectrometer, you needed to know the fragmentation patterns and to figure out what went on. I think it took me several weeks to interpret the spectrum, for example. We also looked at other proteins with modifications. This is again the gamma-carboxyglutamic acid. And you see the combination we used was to use a sequencer, the protein sequencer with Edman degradation, but there we always had gaps, that's the upper line, and then we combined that with trying to isolate the peptides derived from tryptic digest or peptic digest and do the mass spec. And by combining these two, we could get a full sequence of a rather big protein like this one. But the problem was, at that time, the DNA sequencing techniques came along, and I was almost giving up to do any more protein mass spectrometry because everyone was jumping to DNA. And I was also almost doing it, but I loved mass spectrometry and I loved proteins, and I didn't like DNA. And there wasn't much perspective for going into DNA with mass spec. So I decided to stay and wait for a miracle. As a matter of fact, the miracle had been there, but very few of us had realized it, because that was McFarlane's and Torgerson's publication from '74, where they showed what was called plasma desorption mass spectrometry. They had only shown some of the non-volatile peptides, amino acids, arginine and so on, but it worked. And what happened just at the time when I was almost giving up the whole thing, at a protein meeting, I was contacted by a young person in this meeting. He said, "I'm a professor in nuclear physics from Uppsala University. I wonder, do you think it's possible to take a peptide, put it on or a protein, put it on a solid surface, and bombard it with 100 mega-electron-volt particles and get the intact protein up flying?" And I was shaking my head, said, "No way. If we derivatives carefully, if we tickle it with 70 electron-volts electrons, it all falls apart. It will not work." Then he was looking at me and said, "If it works, it is useful." I say, "It would be fantastic." "Thank you," he said, and then he walked away. And 2 years later, in a meeting in Münster, that was a meeting where I first time met one of the other lecturers here, Franz Hildenkamp, and another one, Marvin Westall. He was sitting next to me, and he pulled out of his purse this spectrum and said, "This is insulin based on bombardment with 100 mega-electron-volt particles." I said, "That's fantastic. It doesn't look like a mass spectrum. It looks like a very bad chromatogram." But, I mean, the masses, the peaks were at the right place. So I said to him, and then he asked me, "Would you like to collaborate now?" And I said, "If you want to collaborate with me after I turned you down." "You didn't turn me down. You said it could be useful if it worked," he said. So I immediately got hold of some of the good, clean peptides and went up to Uppsala. And of 13 peptides up to 1.3, 13 kilodalton in mass, the 12 worked. It was absolutely fantastic. It took about 24 hours to record a spectrum. It slowly was growing up on the screen, but you couldn't leave it. You were just sitting there, looking at the screen, excited. "Now I think I can see it," and then it disappeared again, but then it came up again. That was fantastic. And what they used for doing that was a tandem accelerator. And this is the tandem accelerator, a huge monster, several levels below ground level. And at the end of that, in one of the green lines, they had a small time-of-flight mass spectrometer. That's Per Håkansson at the time-of-flight mass spectrometer. And that's where they recorded these first plasma desorption spectra. But then they also knew about McFarlane's work, where the ions were generated by californium-252 instead of with an accelerator. But before that, we worked and tried to see if we could do a real application. And this is the first real application where we are monitoring the synthesis of human insulin based on porcine insulin, where you remove one amino acid and add another amino acid and compare with authentic human insulin. And we also managed to get trypsin up flying. As a matter of fact, we wrote the whole paper before we made the experiments, because Bo Sundqvist and I, we were walking around and making fantasies of what would be possible. And we found out it was easier to write the paper than just make fantasies. And then afterwards, we went to the lab and made the experiments to show that it was also possible. But that worked out. But what happened with the Uppsala group, they tried to make a commercial version of the plasma desorption, where they have the californium source here, and when it fissions, it sends one particle this way and one particle that way. They have the same approximately energy as this 100 mega-electron volt, And this one goes straight through the sample and dissolves the sample, and then you can measure the mass by time of flight. And the prototype, you see it here in the lab. You have Bo Sundqvist here, you have Per Håkansson here, and some of the other people in the group. And that was a prototype. It had a 20 centimeter flight tube, very small flight tube. So the resolution was not fantastic. But they developed the very first commercial instrument, and that's the one here. And we were lucky to get the very first one. We had a lot of discussions of whether we should have tuning and not on such an instrument. So we have lots of knobs, but they were later eliminated because they were absolutely not necessary. It was the most simple mass spectrometer you could use, and I would say it's the first really user-friendly mass spectrometer where you can do nothing, you just put in your sample and get your result. But we had this one, and later we had up to 4 of these standing in the lab. They were running all time because it took quite a long time to record spectra on these machines. It was still, the spectra were not fantastic, but by coincidence, up in Uppsala, someone had put a blotting membrane of nitrocellulose in the plasma desorption instrument, and they got better results. So we found out if we use a matrix, and the matrix is nitrocellulose, then we get much, much more beautiful result. That is insulin based on nitrocellulose, and in addition, the protein was kind of immobilized on the nitrocellulose, so you could do reactions. Here, for example, we have reduced the 2 chains, so we see the B and the A chains very nicely. By that, simply we can record the spectrum of the intact protein and either do reduction or digestion or other things and get more information. Also, I mean, the trypsin spectra were improved dramatically. This was the original one, and this is on nitrocellulose. And interestingly, we get higher charge states. We don't know why, but we just get the higher charge states out of that. And that whole period, I would say, is the best period I've ever experienced in science, because we were a rather small international group of people, including Frans Hillenkamp, Marvin Vestal, Brian Scheid, and a number of other people. And we met and we exchanged ideas totally freely, and we informed each other about what happened. And I still remember, when we come to the subject of today, the day that Frank was calling me eagerly to say, we have beaten you, we have seen a larger molecule by our new technique that you have ever seen. I still remember that point, and I had to admit that Franz was right. I didn't want to admit it in the beginning, but he was right. There was nothing doing. But we had in parallel another thing coming up, and that was FAB, which was Mickey Barber, with whom I recorded my very first mass spectrum at AEI, where he placed also a matrix, that's glycerol normally, and he bombarded, he believed it should be fast atoms, but as a matter of fact, it could as well be ions. But it's called fast atom bombardment, and that also works, and that could be rather easily implemented on a normal sector instrument, which we could not do with plasma desorption. These are some spectra from Mickey Barber. This is from Howard Morris. They were the first ones to have the technique, and because of the large sector instruments, they had a good resolution, so they could even make isotope resolution of insulin with these instruments. They could also go higher up in mass. So this is Eklund C, about 8,000, also by FAB, but the limit was approximately somewhere around 10 to 15,000. Then they couldn't get any further up. But interesting, oh well, I changed, that doesn't matter. But interestingly enough, when we look at it, then there were new possibilities which we could start on. And for example, Howard Morris, he moved in and did what he called FAB mapping, and we did exactly the same with plasma desorption. So you make a digest of your protein and you get the peaks. It's what we today call peptide mass fingerprinting. But that was mainly to characterize, let's say, recombinant proteins. And in FAB, you had to do it offline, but in plasma desorption, you could take the intact spectrum and then do the digest directly on the sample, which we had already analyzed, and get the information. That worked quite nicely. We also because we could still not do real sequencing of larger molecules. So we made a combination of mass spectrometry and Edman degradation, and using this kind of scheme we had here, we could sequence quite good, easily proteins, much easier than with Edman degradation alone. And we have sequenced more than 15 different proteins, partially or fully, using this strategy. Another thing which was striking was that when we looked in the very low intensities in the spectra, both by far and by plasma absorption, then there were some small peaks. And Bo Sundqvist had sent down a guy to me, a medical student, and asked me to put him to do something, because he didn't know what to make him doing. And I said, you go in and look at all the small peaks and see if they're fragment ions. He couldn't understand the concept of fragment ions, so I said, okay, if it's from the N terminals, call it A, B, and C, and if it's from the other end, call it X, Y, and Z. And that was what he did, and that was so easy, so I suggested this nomenclature. It's a one-page paper, and note to the editor, but it's my most cited paper ever. So, I mean, this is really how you can be lucky. But the luck was really the appearance of these instruments. That was a big four-sector instrument where you could do MS on FAB, and this is the typical one which Biban used. And here it was really working then a lot. And here also, if we go one step back, he also found some additional fragment ions, the D, the V, and W ions, which are coming from side chain fragmentation, which we could not see in plasma desorption. But Beeman and a number of other people invested in this huge four-sector instruments. They are monstrous. And I remember I saw one Stephen Carr's instrument when he was working at a company, I don't remember which one, and it was so big that when they adjusted the slits, they had to use a walkie-talkie from one end of the instrument to the other end of the instrument to be coordinated in what they were doing. I mean, that was kind of strange. I fortunately never got money for this instrument, because then we would have been stuck with a white elephant. But Beeman went very far with his sequencing, and as a matter of fact, I think he is the first one who ever completely sequenced a protein by mass spec, but he only did it with one, because it was a hell of a job to do it. But he did it. But we went differently, because the problem was really that we had a lot of sequence information from cDNA sequencing and from the DNA sequencing. So we said maybe we can combine the mass spec information with the information from DNA sequences or RNA, messenger RNA sequences. And so we went in and looked into the pituitary peptides, which are derived from rather large precursor messenger RNAs, which are then synthesized and clipped up. And we could then, by combining the mass with the sequence information from DNA sequencing, we could identify almost all the different peptides, where they came from and how they were modified in this system. And we call that peptide charting, and it's really the precursor of the way we now use when we are identifying proteins based on based in proteomics in general. So that was kind of an eye-opener for us, and we knew that we could do it. And in the coming years, we started to look at DNA sequences and the mass spec. For example, that's one of the first ones where we only had a mass spectrum and a DNA sequence, and we didn't know which DNA sequence would fit to our mass, but we could then combine it with the DNA sequence information and find out exactly which peptide it was and also how it was modified. In parallel, Mickey Barber, he came to our laboratory to test our plasma desorption, and he was very interested in hemoglobins, so we worked together on hemoglobins to find hemoglobin variants. And one of my students at that time, Ole Jensen, who is now full professor, he was kind of going in with that in his master's thesis, and we got hold of a number of variants of hemoglobin, especially from Russia, and we could then characterize him. My job to him as his master's thesis was, I said, I'm 50 microliter of blood, you should be able to identify which variant it is, if it is a variant. And he ended up by being able to do it on 1 microliter. So I think that was quite nice. And it really showed at that time that mass spec was getting into business. But then our whole world broke down in 1988, and that's my introduction to the subsequent lecturers, because in 1988, John Fenn presented the first electrospace spectra peptides at the ASMS conference in San Francisco, and Carlos and Hillekamp showed the first MALDI spectra on the International Mass Spec meeting in Porto. And I mean, that year was really the year where we all said, what's happening now? I remember, I knew that John Fenn would present something, and I called Brian Scheid on one of the corridors and said, are you going to that lecture? He said, what lecture? I said, this is something absolutely fascinating. And we went in, Brian and I think there were 10 people in the audience when Fenn presented this thing. There were very few people, but we both spoke down and said, now the world has changed. And then when Franz showed this, but I knew about that before, then, I mean, we really knew that now things were going. And we were extremely lucky because we were the first laboratory, I think worldwide, who had all 4 techniques. We had our plasma desorption, we had FAB, we had MALDI, because we had changed one of our plasma desorption instruments to MALDI, and we had electrospray because of the courtesy of Marvin Vestal. He managed to get us an electrospray instrument. It was still stated turbospray on the cabinet, but it was an electrospray instrument. And we then could compare what went on, and you can see with 2 nanomoles we could get, that's 11,000 something paralbumin, we could get plasma desorption spectrum. With 50 picomoles and less than 50 picomoles, we could get our electrospray spectrum and the MALDI spectrum. And by working and playing around and with a reflector MALDI instrument, we could go down to 50 attomoles and get a substance P, a rather small peptide, but still. I mean, now it was very clear that we could kind of trash our plasma desorption instrument, we could trash our sector instruments with FAB, and just concentrate on the new instruments. And since that, we have only been using electrospray and MALDI, and most of my students, they love electrospray, but I'm still a MALDI fan, because MALDI is by far the easiest way of getting results. And since this is a MALDI session, I would say, don't give up MALDI. And in continuation of what we had here with identifying peptides from DNA sequences, we came up with how to use the mass spec molecular way to identify proteins. We tried to publish that for 3 years, and nobody would take it. They say it cannot be that easy. And only after 3 years, when a number of other people also had come up with this idea, all these papers were published in the same months. So it was really, we could not convince anyone that it was so easy to identify proteins. I remember I had submitted it originally to BNAS, and Fred McCafferty was the referee, and he said, it cannot be that easy. It's impossible, it cannot be that easy. And you had to prove it more and more, and at the end I got fed up, and I published in biomedical mass spectrometry instead. But anyway, that's what we all do today in proteomics. And with that I would say, how has it developed over the years? Well, with electron impact mass spectrometry, we used about 0.1 micromoles. Okay. I'm moving too much. Sorry. I mean, with electron impact mass spectrometry, we had to have about 0.1 micromole to do something, and we could get to 1 to 1.5 kilodalton. With plasma desorption, we were down to 1 nanomole. That was, say, 100 times better, and we could go up to 20 to 30 kilodalton. With FAB, we were in the same sensitivity range, but we could only come up to 10 to 15 kilodalton. But now, MALDI and ESI, well, there are no mass limits, almost, I would say, and we are down to the femto attomole level. So things have dramatically developed, and the only thing which has not been improved, that's the mass accuracy. The mass accuracy with the old sector instruments was as good as with the best instruments we have today. But the development has been fantastic. And with that, I think my time is up, and I will thank you for your attendance. And these are the people who were involved in the early times in my laboratory, different of my students. The Uppsala group was absolutely essential. And then my colleagues and instrument manufacturers from all over the world who helped me. But I would say the real fantastic thing in that pioneering period, that was the way we communicated across continents and had this. We were all so idealistic, and we had no idea what we were doing. And that was say, when we looked at this spectra coming out, we say, why? How do they come? We were scratching our heads and trying to figure out how was it possible to see these things. So that was, I would say, the most inspiring period of my whole scientific career. That was the 80s. And with that, thank you for your attention.
We have time for a few questions. Anyone?
I mean, there are probably no questions to such a, let's say, a dinosaur historic lecture.
Back here.
There's one, yeah.
Have these new sources been patented, or were they completely freely available?
Well, I think there were some patents, but not that many. I mean, MALDI has never been patented. Electrospray, I mean, Fenn had some patents on the source, I think, but I mean, other people could make sources anyway by coming around the patents. Plasma desorption was not patented. FAB was not patented. And I mean, the mass spectrometers were there. I mean, of course, there were patents of some of the mass spectrometers, but there were ways around it. I mean, the companies are experts in finding a way around the patent. So we didn't feel any limitations, and I think that was very important. And we didn't have a university kind of being on our back to be sure that we would patent anything interesting. So we just discussed openly. We had no pressure from that side. And I think today's situation where universities are kind of trying to be sure that we don't disclose anything before they have the patent is kind of killing a lot of the free scientific exchange. So I think the universities are making a big damage to science by inquiring that everything shall be patented and kept secret for a long time. But I do not agree with our university administration. Any other questions? No? Not really. Oh yeah, there's one.
Can you go back a couple of slides with the so part like this standards, spectrum up on top. I might have a hard time interpreting it. So can you tell me what kind of shape the peak of these?
Well, I mean, this is made with a. Yeah, it's why these peaks have this ugly shape. And it is an ugly shape, but it's made with a 20 centimeter flight tube in a time-of-flight instrument. But I remember when I first time showed at MIT this plasma desorption spectrum, it was in Biemann's laboratory. I had made two presentations, one which looks like that, another one with line spectra as we were used to do from electron impact spectra. And Biemann, I asked, what should I use as presentation? And Biemann's answer was very clear. Such lousy spectra should be presented as they are. Barbie?
I might comment on that because, in fact, it doesn't matter how long you make the flight tube, the ions are metastable, so they fragment in flight. So a lot of that loss of resolution is because the ions are fragmenting as they fly along. So you're seeing an effect of that. Even though it's a linear system, it doesn't have as much effect.
If it's related to? No, it's not really the bin size. The time resolution is good enough. It's really a matter of that when these ions are kicked off, they get some additional energy, and then on the flight they will fall apart, and some ions will part this way, the others the other way. If you have a reflector, you may lose all your ions because none of them at the end have the right energy to go through the reflector.
I will discuss that to some extent in my talk.
Okay.
Thanks again, Peter.
Okay, thank you.